Imagine we have a truck heading toward a car. The truck is catching up, and eventually they collide. Now you may have noticed the truck slowed down, but the car sped up. Let's watch one more time. Here's the truck, here's the car. We can talk about what happens using momentum. The car has momentum and the truck both have momentum at the beginning. And at the end, likewise, there is some momentum because the objects are moving. But what's the total momentum of the system? Initially, it's 12. At the end, then, it also has to be 12 if the system is isolated. So the car, we know, speeds up because it's rear-ended from behind. But that means if the total will add to 12, the truck must have decreased from 10 Newton seconds to a final momentum of 8 Newton seconds. Here's another scenario. Let's say we have two pendulums connected to a ceiling. One has been pulled back and it's released from rest. When the first pendulum is released, it collides with the second, causing them both to bounce back up a little bit. We'll pause it right there. Let's watch that one more time. The first one falls down and it bounces back. Now, we started out right before the collision with this pendulum moving and the other at rest. Because this one is at rest, it has no momentum at the beginning, but the other does have momentum, which we'll make positive because it's heading to the right. What's the total value? 10 Newton seconds, because 10 plus 0 gives 10. Right after the collision, in this final moment, just after, what's going on? Well, if momentum is conserved, then the total value has to be the same before and after. But wait a second. This pendulum is bouncing backwards, which gives it some negative momentum. What do you know about the other pendulum? Is it equal to 10 Newton seconds? Greater? Less? Well, if the two are adding to 10, and this is negative, this pendulum must have positive 13, more than 10 Newton seconds. Time for our final scenario. A person is on roller skates holding a heavy bowling ball. She heaves it forward, and they move in opposite directions. Let's watch that one more time. They start at rest, and she throws the bowling ball forward. Like before, we can analyze using momentum. If they start at rest, neither has momentum initially. The total is 0 Newton seconds. At the end, the total momentum must still be 0 Newton seconds because total momentum is conserved in an isolated system like this one. But wait a second, the bowling ball is moving forward, so it has some positive momentum, like 10 Newton seconds perhaps. So how can the total momentum be 0? She simply must be moving backwards with negative momentum, and they add to 0. What have we learned? It doesn't matter what scenario we're looking at. In all cases, the total momentum of the entire system does not change. The total value is conserved. But how is this possible? After all, the car, if you look back, gained momentum, and the truck lost momentum. The pendulum on the right gained some momentum during this collision. The other guy lost momentum. The ball gained momentum, and the person lost momentum. All of these values were the actual numbers from the prior part of the video. And you can see what's happening here. The reason why total momentum is conserved is because the two changes add to 0. In other words, the total momentum does not change at all. The total change would be 0 for the entire system, both objects combined. Why do these changes exactly cancel out in every case? It has to do with force and Newton's third law. In fact, all of momentum conservation comes from Newton's third law. So during this collision, the truck is getting pushed to the left, but the car is getting pushed to the right with an equal and opposite force. When the pendulums collide, the one here gets pushed to the left, and this is pushed to the right by the other guy. As the person throws the ball, she pushes the ball to the right, so she feels a force to the left, as the ball feels a force to the right. Those forces are all equal, just in opposite directions. Now, you might notice something fishy. I've labeled these F-net. There are other forces acting, perhaps friction, gravity, normal force. When we say the system is isolated, we assume that the net force is just coming from those collision forces. Okay, we understand Newton's third law, but what does this have to do with momentum? The answer lies in impulse. The net impulse is equal to the net force times the change in time. But the two cars feel the same net force, according to Newton's third law. Likewise here and here, the two forces are the same. And the two cars are interacting for the same amount of time. Therefore, they have the same net impulse. But net impulse, we've learned, is equal to change in momentum. Therefore, the two objects that are colliding also have the same change in momentum. Now, the only thing we need to point out, the forces are in opposite directions. Therefore, the delta P's will be in opposite directions too. One will always be positive, and the other will always be negative. So if they're equal but opposite, they will add to zero, and total momentum is conserved.